Starting, all attendees are in listen-only mode.
So, good morning, SCT members and broadband cable professionals. Hopefully, everybody's doing just great today. So, I'm Woody. In case you didn't know who I am, I'm Woody Cash. I'm the Content Knowledge Officer for the Golden Gate chapter. Today, we have Kevin Parise of EXFO. He will be doing our presentation. Kevin has decades of experience, and he's an expert in test and measurement field. Takes a hand-on and virtual experience to training. So yeah, I know that's kind of an irony, hands-on virtual, but he really does. It's really impressive the way he does training. So I just like to talk a bit about the some of the benefits of SCTE membership, and then also talk about upcoming events. So give me just a second here. So some of the online resources of SCT are just vast. So if you're not a member, you just don't get access to those details on the website. So I strongly encourage membership. For most employees, membership is part of the CAP program or part of the All Cables Members program. I know that applies to both Comcast and Charter, which covers a lot, and there's others as well. So if you're not a member, check on your local intranet and see if if that membership is paid for, or you do like me and just pay for it yourself. But I'd recommend checking to see if your company covers it. So beyond the some specifics about what's available online, there's ebooks, there's archived webinars, there's Cortex Virtual Learn, there's lightning mods. So if you just want a 2 or 3 minute primer on a specific topic, you can look through that. And they also have network sim with 3D simulations, so that's quite impressive. If you haven't tried that, you may want to take a look at it. For those that have joined that are Golden Gate members, please check out our certification incentive plan. That's on our website. And not only can you get certified and have credentials that you will carry with you no matter where you're working, you actually get paid to do that. So you're going to learn, you're going to prove yourself, and then you're going to get paid. So that's 3 winning things that you get out of certification. So let's talk about some upcoming events real quickly, and then we'll get started on our webinar. On 7/8, we have our Summer Training Summit, which is 6 days, and
I don't hear your auto anymore, Woody. Yeah, I still don't hear your audio, Woody. Yeah, unfortunately, I can't see any of the audience chat, so I don't know if it's just me or everybody, or if nobody can hear you.
Hello? Hello.
There you are. You're back. You're back.
Okay, it's really strange because if I get a call on my phone, it somehow mutes the audio on GoToMeeting, and then I have to go into the audio settings of GoToMeeting. I forgot that
I
happened one time before, so
love
uh,
technology. Well, perfect.
yeah, yeah. So I'm sorry. I'm sorry, folks. I'll just talk about this real quickly. We have the Summer Summit training begins on 7/8. We start off with Fiber to the Home with Dick Robinson, and we have a 6 total days of training. A lot of people are signed up for that, so we have a lot of training sessions. On 9/9, we have DOCSIS 4.0 with Brady Volpe. If you've ever listened to Brady Volpe, what an outstanding presenter he is. So that ought to be very interesting. And then on 10/7, we have FDX. That's the bolts of FDX with Frank Eichenlaub. And then 11/4, we have powering critical infrastructure with Intersys. They're going to be doing a topic we haven't done before, so I'm really looking forward to that. Well, with that, I'm going to turn it over to Kevin, and hopefully you don't have the technical difficulties I did.
Good deal, Woody. Thank you very much. I think I'm already sharing my screen, right? Do you see my my deck?
Oh, yes, I do see your deck.
Okay, perfect. And then you should see my face here in a second.
Okay.
So hopefully I got it shared right.
Great.
Perfect. Don't mind my
Yes.
messy office back here.
Yeah, I definitely do. And yeah, hopefully nobody paid attention to my background. I wish there was a background blocker here.
Nah, you're fine. You're fine. You're totally fine. Okay, so my name is Kevin Pierce with EXFO, so I do a lot of the training for EXFO. And so today we'll be doing fiber network troubleshooting tools and techniques. It's going to have a little bit of what I've talked about in the past, kind of remedial stuff, the first 15 minutes or so. And then the rest of it's I'm going to be plugging in equipment, showing you some typical troubleshooting steps and techniques and those types of things. And of course, if you have any questions, ask up, and Woody will share that with me, as we go along. So let's go ahead and kick it off here. So from a high level, just one disclaimer I started to put basically is, a lot of things I talk about, some of the values and thresholds are just kind of some common ones that I see within the industry. But you want to make sure and validate, any of the information like splice loss, ORL, acceptable value, those types of things. You make sure that you validate all that information first, with your company. And this isn't standard. That's kind of a little legal disclaimer that I got there, basically. So we'll talk a tiny bit about fiber theory, just really high level stuff, just enough for us when we get to the using the tools, it'll make more sense. And then we'll get into OTDR theory, not just OTDR, but just theory of testing in general. And then from there we'll kind of summarize it and take any additional questions at the end that we might have. So just again, really high level, when we're talking about fiber, obviously there's a lot of different types of fiber out there, but from a testing perspective, really what we're worried about is, the cladding and the actual core itself, right? These are the two portions of the fiber that we're worried about, that optical conduit that is used for transmitting our signal down the fiber and those types of things, right? And so we're going to be talking primarily about single mode fiber. There is multi-mode fiber, but really the intention here is single mode, which is what most of you will be dealing with. And so, oops, went backwards there. And so when it comes to fiber, one of the first things we talk about is just, proper handling and care. The obvious things, don't touch the end of the fiber, use your protective caps, which I'm very bad at, right? I mean, a lot of my stuff, if you were to look at my office here, I got half of my stuff, I lose the caps. They're somewhere, they're on the floor. The vacuum cleaner eats them up. But hopefully you practice better habits than I do in my home office here. And so, just and pay attention to the routing of the cable, right? Bend radius and things like that. So when you're running new fibers, a lot of these things are things that you need to understand, because a lot of maintenance issues are often installation issues, right? Something that wasn't caught during installation qualification, you try to turn up a new circuit, you're getting additional loss, you're getting some noise on the fiber, retransmissions, whatever it happens to be. So you want to make sure that proper fiber handling is something that you're really taking care of. And we'll share this deck with you after as well. But again, a lot of these things are pretty obvious, but I think it's important to talk about, just taking care of what you're doing there. And from a testing and troubleshooting perspective, it's really important to have accessories. So for those of us that do troubleshooting, or those of us, that are technicians, we have a bag full of just accessories and things that make our lives a little bit easier. And there's all kinds of different tools. I have a wood shop, and I work on cars down in my garage quite a bit. And so there's a lot of specialized things that I put together and use on a regular basis. And from testing, that's the same thing. Having additional couplers and attenuators and, ways to inspect and clean fibers is critically important. So having all of this stuff within your toolkit is valuable. I also would like to add in here for bulkhead adapters is I like to use a lot of ones that will change the gender of the actual fibers or the type. So LC to SC, those types of things. If you can get one of those hybrid adapters, those are useful as well for those situations where you roll up somewhere and all of a sudden it's like, I don't have, that particular type of connection. And then having, of course, a bunch of extra jumpers. Ones that match your test sets and all the different types of applications you might have. And so having all these things within your toolbox is important. So when we're actually testing, and what we're going to be troubleshooting is going to be these 3 critical parameters that I talk about quite a bit in all my seminars. We're going to be talking about how to qualify insertion loss. And insertion loss means this is the loss that you insert into the fiber. Splices, connectors, muxes, those types of devices. Those are all insertion loss devices. So we'll talk about how to troubleshoot that with an OTDR or an advanced OTDR. Issues with placement. So macro bends, exceeding the bend radius of the fiber, cable compression, and how fiber management and the care that you take in managing your fibers is critically important as well. And then reflection and ORL, which is a huge one, especially within the MSO environment. Back in the days of RF analog video, when you're, cascading EDFA amplifiers and you had a lot of output power, this is the type of stuff that would cause, interference and noise on the system. So things like tiling and retransmissions and stuff like that were often attributed to reflection or ORL, which to me is essentially what generates additional noise in the system. And I'm not talking electromagnetic noise, right? That's more of the world of coax and twisted pair. I'm talking about optical signal noise ratio, so OSNR. And so SNR is something that you're very familiar with, back in the the coax days, and of course still today as well. But this is optical signal noise ratio, and one of the principal issues that we see in a system that causes issues with OSNR is going to be reflection, right? Reflection and ORL, and we'll talk about what those are and what the differences are between the two. It's also important to understand dB versus dBm when you're testing. If you're doing loss testing, checking span loss, if you're looking at connector loss, splice loss, that's dB. It's a relative measurement, right? That's dB. dBm is absolute. This is when you're measuring power. And the reason why I talk about this is because one of the first mistakes I made, when I came over from construction, I used to, do placement. When I came over to craft, one of the first mistakes I made on the operations side was setting my power meter wrong, which is one of the things I'll show you when I plug a power meter in. dBm is power. dB is loss. One's a relative measurement, one's an absolute measurement. If you want to measure the power level coming into a remote PHY device, into a fiber node, that's power dBm. If you want to measure the difference between the signal coming in and the signal coming out, that's loss, right? And again, that's just something that I like to talk about because it's important to distinguish them. And then it's also important to understand the impact of loss on a system. And I like this slide quite a bit for every 3 dB of loss, we lose 50% of our incoming signal, right? So for every 3 dB of loss, we only have 50% light left. So if I had, say, fiber number 1 here and fiber number 2 at a patch panel, and number 1 had 20 dB of loss, and number 2 had 23 dB of loss, this is a 50% difference in power, right? So for every 3 dB, and you notice here, you go to 6, you're down to 25, right? And so as you double 3, 6, 9, you're starting to double your loss. In fact, if you look at the specs of splitters, if you deal with passive splitters, 1x2s, 1x4s, 1x8s, except for the connector, the splitter losses, this is going to be 3 dB, this is going to be 6 dB, and so basically this is the loss every time you split it, not including the connectors, right? You're going to have connector loss as well, but so it's important to understand that's what's happening there. So for every 3 dB of loss, you're going to have, you lose 50% of your power. For every connector, most connectors for pass fail are at half a dB. So every time you add a connector and it's near half, if it's half a dB, you're adding a little over 10% of loss, of power loss. Most splices fit somewhere in here. Right? So you want to minimize these as much as possible. While your connector max might be 0.5 dB at 1550, the typical, depending on the manufacturer, it could be somewhere around 0.2, 0.3 dB. Hopefully you're closer to the typical because every one of those tenths of a dB adds up, right? It adds up over time. And so the critical parameters we're looking at, we're not going to be looking at dispersion today. Dispersion is advanced optics. It's an important discussion, but today I'm going to stick to your day-to-day troubleshooting, right? So dispersion is when you start testing for DWDM, when you start testing for high-speed traffic, qualifying your fiber for those types of technologies. It's an important discussion. Maybe that's something that we can have in the future, more advanced optics discussion for those that want to talk about dispersion. It's a really interesting conversation. We're going to focus on the two big ones: attenuation and optical return loss. And optical return loss and reflection go hand in hand. I'll explain how they're different and how they're alike. Attenuation, power in, power out, right? Simple stuff. And return loss, or optical return loss, is light that reflects back and is what creates noise in the system, right? So we'll talk about the difference between those two. And we'll start with attenuation first, right? So attenuation, power in, power out type of stuff. Intrinsic attenuation, so we expect about 0.2 dB of loss per kilometer, at 1550, and about 0.35 dB of loss at 1310. All right, so this is what we expect for those fibers, roughly in that area, right? So if I have 100 kilometers of fiber, which is like 60 miles, it'll be 20 dB versus 35. And so that's 15 dB delta between the two wavelengths. So 1310 is quite a bit loss here. So a lot of your old systems where you're pushing, traffic or bandwidth to, say, a fiber node somewhere, if it was fairly close by, 1310 down, 1310 up. But as you start extending your reach, then you start looking at 1550. If you go to DWDM and you're muxing your signals, you're going to the C-band range typically. If you're doing BiDis, so bidirectional transceivers to recover that extra fiber, you might have 1490 down, 1550 up, or 1550 down, 1310 up, right? So it's important to understand that intrinsically they have different loss per kilometer. And here's a little slide that talks to some of the differences in the different wavelengths and stuff like that. And so I just mentioned this right here. Extrinsic is externally influenced attenuation. This is splices, fiber management issues, pinching, compression, connectors, those types of things. This is what we're troubleshooting quite a bit, right? Looking for problems, damages in the cable, looking for opens, those types of things. These are externally influenced attenuation, and this is what we're going to look at. And for connectors, typical pass-fail for loss on a connector is 0.5 dB. Yours might vary. Some of the newer high-performance connectors are getting, down to 0.35 max. So you might start seeing some variations in some of those thresholds. But again, as I mentioned earlier, refer back to your company's practice to make sure what is acceptable value here. So of course, as the signal crosses a fiber, it loses power. up to half a dB is what we're looking for. And so we're looking for that, and we're looking for issues with splicing. And typical for splicing, it could be, I typically see between 0.5 and as high as 0.3, depending on who who you're working with. I like it to be around 0.5, 0.2 in that range, to minimize it. So this is, looking for loss going across your splices there. And of course, bending or cable compression in the system. This is fiber management issues. And so I will use an OTDR to show you how to troubleshoot all of these things, right? So we'll come back to fiber bending and macro bending and those types of things. In fact, I'm going to skip this slide here because I'm going to show you this, how wavelengths react differently to pinches in the fiber, right? The longer the wavelength, the more issues you're going to have with compression and exceeding the bend radius of the fiber, so your fiber management issues, right? So I'll show you that as well, within that. But once you understand what the acceptable values are, you can put all these numbers together, right? You can put all these values together to do a quick link budget. What's my acceptable loss going across the span? And you can evaluate that, what your minimum and your maximum optical budget is based on all those things. And so, and these are things you can validate, that you will be validating with tools like the OTDR and the OLTS and those types of things that we'll be plugging in and talking about here shortly. And so let me get my timer up here so I make sure I don't exceed my time, which I have a bad habit of doing. There we go. And so it's really important to understand that, that's what's happening with some of these issues. So when I plug in the unit itself, it'll make a lot more sense to you, right? It'll make a lot more sense. And then of course at that point you can do your link budgeting. In fact, I'm going to go ahead and show you the macro bending now because we're on this topic. And again, this is still Fiber 101 stuff. And so going back to this one slide here, the longer the wavelength, so 1550 is 1,550 nanometers is the length of the wave. So it's a larger wave than 1310. And 1310, as I mentioned earlier, this is all the stuff that was, feeding your existing system. So this might feed a remote PHY device out somewhere. You have 1310 down and you have 1310 up. Fairly typical. This might be, a 20-kilometer span, whatever. But let's say that you're running out of fibers on that, in that region. Somebody built a new subdivision. There's a data center going up, whatever, right? So all of a sudden, this area over here needs more bandwidth, but you're running out of fiber. Well, there's several things you can do. One is you can go to BiDIs, bidirectional transceiver, so transmit and receive on the same fiber. And so now you're doing bidirectional here. And so you're transmitting and receiving on one fiber, so that means now you're recovering 50% of your fibers that you can do more with, right? Of course, it adds complications. Now you have to be careful, but fiber, transceiver mismatch, SFP mismatch, those types of things. But all of a sudden, instead of doing 1310, in both directions, you're going to do 1310 down and maybe 1550 up now. Because it's BiDi. Well, look what happens to 1550 over here. It takes a huge, drop there. So it's got a lot of loss. That loss didn't exist with 1310, but it exists with 1550. So now your upstream signal has to go through extra attenuation. And what's happening here is we have a pinch in the fiber, is essentially what it is, right? So we have a pinch in the fiber, and I'm going to show you that. Let me switch to my camera here. So basically what I'm going to do here, I have an OTDR over here, which actually I'll log into. So let me log into the OTDR real quick here. Forgot to log into that sucker. So let me that go. And so while the OTDR is logging in, I have a jumper over here. So I have about 15,000 feet or something in that range here, all set up. You know what? Give me a second. I'm sorry. For some reason my OTDR is not online. Let me set that up. It's my turn to have a hiccup here. But essentially what I'm going to do here is I'm going to pinch the fiber about 500 feet out or in that range. So about 500 feet out, I'm going to pinch the fiber and I'm going to, there's the problem. There we go. And this fiber pinch is going to be about 500 feet out. So this is a Sam Charlie UPC. I know you're primarily APC, but in this example, this will work for us here. And so I'm going to pinch this fiber, and let me go ahead and log it back into my test equipment here. And then share that screen with you. There we go. So, oh, you're not seeing it. So basically what I have is I got my OTDR logged in here. And right here at number 2, this is this blue connector that I had up here. I'm going to go ahead and do a quick test, and we'll come back to the OTDR here because this is more for the troubleshooting side of it. I'm going to do a quick test at 1310 and 1550, and I'll do another one at 1650, just so we have 3 of them here, right? And I'll do a quick test just to get a baseline. And so I haven't done anything to the connector yet. And this is just a bunch of launch cables daisy chained together is what I have here, essentially. And so once it's done doing all 3 wavelengths, we'll come back and analyze the difference in loss between them. That won't be much unless there's already a pinch in the fiber. So I'm going to go over here to event number 2. And so if you look at event number 2 here, it's at 517 feet. It has about a half a dB of loss. We'll come back to what reflection means. That's at 1550. So half a dB at 1550. 1650 is also half dB, roughly. And then 1310, it is 0.8. We expect 1310 to be a little bit higher, right? Which we talked about earlier. So now what I'm going to do is I'm going to push my camera here to the down camera. And let me change something here. I'm going to change the setting here real quick in the OTDR. And so what I'm going to do now is I'm going to pinch this fiber. So I'm going to pinch this fiber, probably about that much there. So we'll do a pretty decent pinch. And then I'm going to switch back to the OTDR. And so with the OTDR, I'm going to retest this with that pinch in there. And remember, it's that one at number 2 that was, between 0.5 and 0.8 dB. Now look at 1550. It just drops like a rock. I might have pinched it too much. And 1650 is gone altogether. And 1310 has lost, but it still makes it through, though. And so the longer the wavelength, the more issues you're going to have with cable compression and pinching. So, at 1310, we're going to have some decent loss here, 1.9. So 2 dB of loss at 1310, which is high. 1550 is going to be 7.4. So we've lost 50% on top of 50% plus a little bit more power. So it's completely useless. And 1650 is gone. It doesn't wake up after the 500 feet because it's even a longer wavelength. And as I mentioned in some of my other videos, what's happening here is, the fiber core is maybe 8.2, 8.3 microns. When you pinch the fiber or compress it, it changes the core size. And the longer wavelengths occupy more of the core, even a little bit into the cladding. And what happens when you compress it, the longer wavelengths have to burn their power to get through that pinch. And so for years, you've had that system with that 1310 feeding that remote PHY, and all of a sudden you want to upgrade it. And somewhere in the path at 500 feet, maybe a volt splice, there's a fiber management issue or a cable compression issue that's creating attenuation that, while it affected 1310 was still able to get through. So maybe 1310 was working just fine. So this is a installation issue that wasn't captured during qualifications, right? Or something that happened after the fact. And so that's why it's important to test multiple wavelengths, and it's important to understand the theory of the fiber, because now we're going to be troubleshooting with stuff like this, right? And so that's important to realize and understand. And so that's one of the big things. And so, as we're troubleshooting, I'll come back and talk about that more when I plug in the OTDR and we start doing, a little bit more advanced stuff with the OTDR there. And so that's attenuation, right? That's attenuation. It's power in, power out. How much power am I losing going across the span, across the connector, or across the splice, right? Then we have optical return loss. or reflection. This one is really important to understand. Because when it comes to the testing that we normally do, the number one tool, in fact, every single person that touches fiber needs to have a minimum of two things: a power meter, and if I can find one here, the fiber inspection probe. And there's different versions, right? So a power meter and a fiber inspection probe are critical because you have to have some way to measure light, right? It's like an electrician showing up without a voltmeter, without a multimeter, right? This is our tool, but it's not a perfect tool. And so what I mean by that, so I'm going to go ahead, I'm going to send myself some light here. Let me turn something on. And what I'm going to do is I'm going to send light to my power meter just to show you what I'm talking about. And so this is a common technique or trick that you use with OTDRs. So let me plug in a source here. So I will send myself some light. Give me a second. I'm going to plug a bunch of stuff in here and pretend I cleaned them. We'll come back to that. But essentially what I have here is I have just a standard power meter. So this is the PX1. So many of you have this. There's different versions of this. There's different versions of power meters in general. But, power meter, we're talking more along the science of this stuff, right? And so essentially what we're doing, and I'm going to go ahead and just be good and clean this off for us here, right, a little bit. So basically what I have here is I have a power meter. And then within this power meter, I'm going to have a connection, right? So this one happens to be LC. I'm going to switch this out, hopefully, if I got one here, to an SC. Yep, there we go. I'm going to switch this to a Sam Charlie. So making sure that you have the right adapter tips is important. So when you are sourcing your tools, that's one of the things you have to take into consideration. So do I have all of the different tips that I need? Because sometimes you'll need a Sam Charlie, sometimes you'll need a Frank Charlie or an LC. In this case, I need a Sam Charlie. And most power meters are open detector, so they can be APC or UPC, right? So in this unit here, I'll turn it on. And I should be sending light down this fiber here. We'll find out here in a second. I'm going to unplug from over here. And so one of the typical troubleshooting things that will happen for you is you'll get a call from an operations center, from your whoever's doing your alarming. And they'll call you and say, hey, Kevin, I need you to go out to, Lafayette, and I need you to go to the head end there. Or I need you to go to this remote PHY. We have some sort of an outage. One of the very first things that you'll do is you'll show up on site and you'll plug in a power meter, right? You'll set it for the wavelength that you need to set it for. So on this particular unit, I can touch it and hit 1550. I can set favorites. This one is even granular down to the ITU channel. So if you are, if you need more granular power, you can have it set. In this case here, I'm going to send myself a 1550 signal. And so I'm going to take this, inspect and clean it, plug it in, and then now here's my first mistake. It says 12.38. Remember I told you when I was first at Tech, I had it set wrong? So this looks like I have a lot of power coming in. In fact, too much power coming in. 12.3, but it looked over here, it's dB, not dBm. I'm measuring loss, not power. I need to tap the unit here and make sure I have it set for dBm. And this is the output power. This is my receive power coming into my card. And -7 is good power for just about every system that I know, right? And so I don't have a power problem. But why am I taking errors? So what do? Well, you start cleaning fibers. Why am I cleaning fibers? I'm not cleaning fibers to improve this. This is fine. I'm cleaning fibers to improve reflection, or ORL, which is noise. A power meter only measures power. That's half of the critical parameters we need for a connector. It only measures power. Just like, if you have a water line, you only measure pressure. But you don't measure the quality of the signal or the amount of noise, the taste, how good does that water taste, right? That's a different test. So if you want to check for the quality of the signal and the amount of noise that's being generated, you need a reflectometer to do that. So this is one of the common issues that you need to understand with a power meter. It's a great tool. It's given us power, but this doesn't necessarily mean the signal is clean. It just means it's got sufficient levels of power. That's it. So keep that in mind, right? That's one of the important things. So we'll talk about how to troubleshoot reflection. And you need an OTDR or a different type of tool to do that. And so this is one of the first things that this is one of the primary tools that you'll be using, as you're testing. And so that's important to understand. Let me go and kill that light there and go back to over here. And so that's power. So we know how to use a power meter to troubleshoot that stuff, right? It's a fairly simple device. Just make sure you have it set right. And then of course and remember that this power meter here, let's switch back over to here. This power meter here, this is a broadband power meter. It's not channelized. So if you have a CWDM system or if you have multiple channels, you're measuring the wavelength range, right? And so you're measuring the entire broadband signal. When you set it for 1550, it just doesn't offset. It doesn't pull 1550 out of the test, right? And so you set it for 1550, but if it's 1310, it'll still show a measurement. It'll just be off because you don't have the right offset set. So this is a broadband power meter. If you need to look at specific wavelengths, then you need something like a channel checker, which I think I have one here. I have a lot of stuff here. A lot of stuff in my home office. So this is a dirty channel checker here. But this one here does, has a C-band DWDM channels, right? So it'll separate the individual channels. So, you want to make sure you have the right kind of tool for that as well. But that's power and attenuation. Reflection in ORL is typically caused by connectors, right? Probably 80% of the maintenance issues out there that we see are dirty connectors. A lot of the fails for construction qualification using OTDRs and IOLM is a dirty launch cable, right? Connectors are a big part of maintenance issues within an optical network. As you amplify your signal, as you add higher speeds, it becomes more of a problem, right? So you want to make sure and have a way to inspect and clean your connectors. What causes reflection? Well, that's an air gap. Anytime there's an air gap in the fiber, you're going to have some level of reflection, right? You're going to have some level of reflection going across that. And, if you stand in front of a window and you look out and it's a bright sunny day, you can see your reflection in that window. The reason why is because there's a change in material type. You're going from glass to air on the other side of that window. And that change in material type will reflect light back. And colors are just wavelengths, right? So red, if you look at a VFL and look at the specs on a VFL, right? And so I think I have a VFL. Yeah, I have a VFL here. So if you look at the specs on a VFL, if I can find it, I need my glasses for this probably. It may say it there. We'll see. I don't know if I can focus on that or not. Probably not. But basically, in this label that we can't read, it's going to tell you what the wavelength range is of that red light, and it's going to be somewhere between usually about 640, 680 nanometers, right? And so there's some good writing. So 640, 680 nanometers. So it's a wavelength. Where blue is like 480 nanometers are in that range. These are wavelengths. They're just wavelengths we can see. And so we can see red, we can see orange, we can see yellow, we can see green, we can see indigo, blue, indigo, and violet. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. The colors of the rainbow. These are wavelengths that we can see. And so infrared is this side of red. Ultraviolet is this side of violet, right? And so if this is 680 and this is 480, so anything less than 480 nanometers is we're getting into the ultraviolet, right? That's where bats can see into ultraviolet, right? Infrared, well, snakes can see into infrared. So, but we can't. We fall in between, right? That's the range that we can visibly see. So that's what's reflecting. Those are the wavelengths that are reflecting off the glass that we can see. And so anytime there's an air gap in the fiber, that's what we're going to have. We're going to have reflection. And on an OTDR, that's that spike on an OTDR trace. That's reflection. And so anytime there's a change in material type glass to air to glass, so physical connection, or mechanical splice, but you shouldn't be seeing too many of those. You're going to get some sort of reflection. And so it's that air gap that causes it. And this is what we typically see. So we have the loss values are the same, but the reflections are different. APCs are neg 65, UPCs are neg 55 at spec. Most companies are doing minus 50 or better for connectors. Again, refer to your practice for the real number. So that's reflection. This is light that comes back towards the transmitter. All right, this is light that comes back, and we don't want it coming back. We want to minimize that as much as possible. If you disregard the negative, the higher the number, the better. So neg 65 is better than neg 55. And in an MSO world, green connectors you lived and breathed by. I came from the telco world, and we were blue. Until fiber to the home, telcos were blue. Once fiber to the home came into place, they went to green. Why? Because the original fiber to the home had RF analog video overlay. And this required amplification, as you well know. So when the telcos got into video, they had to start looking at APC connectors because APC connectors have less reflection, so less noise. And amplification exacerbates noise. If I take a garden hose and hold it to the wall and slowly crack the faucet on the garden hose, low pressure, low power, the water's going to come out, hit the wall, and kind of run down the wall, right? Not a big deal. If I increase the pressure of the water, power, it's going to come out of the garden hose much faster. At a higher pressure, it's going to hit the wall harder, and it's going to splash back in my face, reflection, and that's going to cause noise. So as you increase your amplification, you're going to have more issues with reflection. And so because you're hitting it harder, I'm throwing the tennis ball harder at the wall, it's going to come back and hit me in the face a lot harder. So any reflection near a transmitter will kill a system, right? Will kill a system. And so you really got to be careful with that. And the reason why APCs are better, well, UPCs have a flat cleave, right? A 90-degree angle. So when the signal comes in, when it reflects back to the same optimized angle, and we don't want that. This is your neg 55. Where APCs, on the other hand, have an 8-degree angle. So when that signal comes in, it's going to change the return path. So pool table physics, it's going to change the bank angle, and it's going to come back at a bad angle, and it'll refract into the cladding, or it'll run along the edge, because now it doesn't have a good return. So if you take that same garden hose and all of a sudden the wall's got a tilt to it, it's going to hit that tilt, and most of the splash is going to go down and not back. That's what's happening. That's simple, physics there. I mean, it's very simple as you can get. That's why APCs are better. And that's why you use APC connectors, is because you want to minimize the reflection as much as possible. That's why we have APC on most of our transmitters within our test gear as well, because it improves the performance of our equipment. And so that's the big difference between APC and UPC on neg 55 at spec and neg 65 at spec. And this is considerably better. Considerably better. In fact, it is this much better, which seems low, but remember, we're dealing with, with the quality of the signal here. So that 8-degree angle that we have on here really helps. So when we interface with the other side, we're going to have the same thing, right? We're going to have that 8 degrees, so it's going to change the return path, as opposed to having something that's, essentially flat across here. And so over time, they've had to improve the connector reflection. And so APC is the best. There's the least amount of reflection. And you'll visibly see it on the OTDR. You'll visibly see it on the OTDR, which is pretty cool. So when we get to the OTDR, I'll talk about that. That's reflection. So reflection is the specific, is the amount of light returning from a specific location. So reflection is how much light is coming back from this connector. How much light is coming back from this connector? It's a negative value. So it's the value at a very specific location. Optical return loss is the reflection across the span. Let's call it span reflection. And so what it does is it adds up all the reflection intrinsically in the glass. It adds up the reflection from every connector, every splice, and then it gives us a positive value. And intrinsically, reflection will build up in the glass. So if I have 1 meter of fiber, that's about 70 dB of ORL, optical return loss. If I go to 10 meters, I go to 60. 100 meters, 50. 1,000 meters, 40. You kind of see the math here, right? But after a certain distance, and I'd have to look it up, but probably like 3 kilometers or somewhere in that range. I really have to look it up. But to infinity, the signal never gets worse than 32. And the reason for that is, as the fiber gets longer, it builds up more attenuation. So as that reflection, as you send it, you got reflection coming back. You send it, you got reflection coming back. You send it, and the reflection is too weak to come back. Right? It's too weak to come back. So what's essentially happening is, you know, if I throw a tennis ball really hard at the wall, it's going to hit the wall and come back to me. If I keep backing up and throwing it just as hard, eventually I'm going to hit the wall. It's going to bounce back, but then it's never going to make it to me because it's too weak to come back. So ORL should never get worse than 32. When you're troubleshooting this, I'll show that to you and how to find that value. This is also the spec for video. So most likely this is your pass-fail spec. It should never get worse than 32. If it does, it's because there's a connector that's bad. There's a connector that's bad, and you need to find that connector and resolve that issue, which is what we'll do with the other tools. And it's a unidirectional test. So you test it A to B and B to A. So you got A to B, and then you got B to A, right? And it's a positive value, and it should be 32 or better, right? And so let's say that I have a connector here, and this one is neg 20 dB. And let's say that for some reason, and over here we're at neg 70, and over here we're at neg 80, whatever. Neg 50. So testing from the B side, my ORL is going to be about 20 dB. Or testing from the A side. Testing from the B side, my ORL is going to be right around 32. Well, why is the B side better? Because it's further away from the noise. You know, me throwing the tennis ball and it bouncing back, right? On the A side, we're right on top of it. Usually, we don't want any high reflection in the first 2.5 kilometers at least. And if you're doing a heavy amplification out to 20 kilometers or more, you want to minimize the amount of reflection close to your amplifier and close to your transmitter, because that's what's going to create the noise. And it only takes one connector, one high reflection connector near your transmitter to tank your ORL, right? And most systems get upset near 27 dB, and many of them quit working at 24 dB. It will depend on the different equipment and type of technologies being used, but these are pretty common values here, right? And so just from a dirty connector, but we don't have a power issue. We have a reflection issue. So that's why the power meter might not catch it, because you can have high loss but low reflection, and you can have high reflection but low loss, right? And again, you need to keep that value. You know, for some folks want the old value was 27 or better because of OC192. Now most companies are going to be 29, 30 to 32, right? And so that's what we typically see. Again, and it is unidirectional test. So that's the difference between reflection and ORL. Reflection is the amount of light being reflected from a specific location, right? Where optical return loss is your span reflection, and it's a positive value. The higher the number, the better. So 32, 40, 50, that's better, right? And so it's important to be able to troubleshoot that and understand that, because when you look at the end face of a connector, in fact, let me turn on the power meter here. I'll show you what I'm talking about. And what I'm going to do is I'm going to go back to the OTDR. In fact, I'm going to shoot an OTDR trace here. So let me go back to the OTDR. Let me see here. Switch my my screens here. Let me go back to the OTDR. So I'm going to go back to the OTDR. I'm not going to do 1310, or I'm not going to do 1310 anymore. I'm just going to do 1550 for the sake of time. And I'm going to go ahead and test at just 1550. So I'll do a quick test at 1550. And, well, you know what? I got to plug the fiber in. 1 second here. Remember, I unplugged it to check the power. So let me go ahead and clean a fiber here real quick and plug it in. There we go. And so I'm going to go ahead and do an average test here. So on an OTDR, and we'll come back to this. This is distance and this is power, right? And so I'm going to go to this first connector here. And it has about 0.6 dB of loss and 0.48 dB of reflection. And so I can try to improve this, right? So if I go to this connector here, it's this one right. Let me switch here. It's this one right here. So I'm going to do a quick cleaning. Having good cleaning equipment and good cleaning practices, it's crucially important. There's a lot of convenience things like real top cleaners. You have one clicks and those types of things. These are convenient, but these are dry methods. And so it's not necessarily bad, but it has its own problems, right? If there's a piece of silica on there, you might scratch it. If there's oils on there, the oils, don't really come off very well. It causes a static buildup when you use the dry methods. Nothing wrong with it, but I'm just saying, just keep in mind the use cases there. What I prefer, and this is just me, I prefer a hybrid method. And within your practice, within your company, you might have a hybrid method. So I like using a dry tissue and then some sort of cleaning solution, right? If you have a pen, these are very convenient. So these are very convenient to put in your pocket, right? But if you get a dry tissue, that's convenient as well. You can also clean your glasses with it. And so this one here, if you just dab it, it'll put it'll add some solution on there. And what I do is I hold in the solution on the wet portion, and then I pull into the dry. And I'll scoot over and do the same thing. I'll do that a couple of times, right? And hopefully that cleans the connector. I'm going to go ahead and just plug that into here. So hopefully I didn't bang it around too much. And then I'm going to use fiber inspection probe. I'm going to use this one right here because this one I can share on the screen. So this can be wireless, but I got it wired right now just because it's less to deal with. So I'm going to go ahead and launch my fiber inspection software. So, and then we're going to analyze this connection right here, and then we're going to retest it to see what it looks like. So we'll go ahead and let it go. Wait for that software to start. Let me go here. Over here. So once this starts, I think I have the probe on. We'll find out here in a second.
While we're waiting on that,
Sure.
Kevin, I'd like to reiterate 2 important points that you've made so far, just for the audience. I know in my experience in field operations, I saw a lot of techs get very confused when they had a good power reading, but things weren't working. So keep in mind that dirty fiber connectors are still probably one of the greatest causes of failures out there. Of course, we're used to fiber cuts. We know how that fails. But if you have good power, yeah, don't be afraid to look, start cleaning fiber connectors. And the other thing that adds to that confusion, if you clean it, do a dry cleaning method, and it doesn't really clean it, you assume that it's clean because you cleaned it, and it still may not be clean. So, yeah, the wet dry, I have to say, is by far the best. And then also inspecting that fiber connector is also really important. Until you inspect it, you cannot assume it's clean.
Yeah, absolutely, Woody. And that's a great point. Or if it's damaged, because if it's damaged, you got to replace it. And it is a large. In fact, when I was a tech, and somebody asked me what I did for a living, I said I swap cards and I clean fibers. And swapping card often cleaned the fiber. this card wasn't bad. It was the fiber within, because back when I was a tech, it was fixed optics, right? We didn't have these fancy SFPs. And so, yeah, and so that's, as you said, it's one of the biggest problems. And so, and often you have good power, but bad reflection. So in this case here, if I were to inspect this connection here, I'm gonna go ahead and plug it in, kind of let it do its thing. So I have it plugged in here. So it's the auto centering, autofocus, all that fanciness. Now my connectors I've seen better days, because I do a lot of, I scratch them all up. Now this one, what probably happened here is I have really bad depth perception. I'm not gonna lie to you. I got one bum eye. So my depth perception not very good. And I mentioned when I plugged it in, I was like, I hope I didn't bump it, because I probably did bump it trying to get it back, get it into here. And so I can try it again. This time I'll just do a clean top just for the sake of time. I already did the wet to dry. And the reason why I like wet to dry is because, if you ever cleaned a window with a dry paper towel and there's oils on it, you're not really getting the oils off. You wait a couple of days and all of a sudden there's dust building up on the oil. And to me, that's kind of the same thing. So I'm going to go ahead and I did a quick cleaning. I'm going to go ahead and plug it back in and see if this did a better job. It did a better job. Now, all this pitting and stuff probably is going to remain here, because this could be my jumper. The more you plug jumpers in and out, the more you get a chance of pitting. Oh, you're not seeing it. Sorry, let's change it here. The more the chance you see this pitting. Yeah, right. So if you double click on it, it turns the overlay on and off. So here's the fiber core itself. We don't want anything landing in the fiber core, right? We don't want anything landing in this fiber core at all. If we do, it's going to be a fail. So we don't want anything landing in here. If you notice, some of these are green and some of them are red. Why? Because based on the spec, we allow up to a certain size. And so this is the cladding. Most of the signal travels in here, right? A little bit travels in the cladding. Anything that lands in here, especially if it's a dark material, this will cause loss. Anything that lands over here of significant size, because this is actually where it touches. The fiber rounds off. It only touches for a small section of the fiber core, right? So anything that lands within the physical area where it's flat and it touches, if it's of a certain size, so the assumption is if it's 5 microns or larger, it could have some mass to it. If it's tiny, like 1 micron, well, it's not going to be very tall. And it's not going to cause much core separation, because it's not going to be 1 micron wide and 10 microns high, right? So that's the assumption. It's a 3-dimensional problem, but we're looking at it 2-dimensionally and trying to make some assumptions. Anything out here will cause core separation, and this is what makes reflection worse. But reflection doesn't need much core separation. So that core separation is going to be minuscule. And the power is not affected by it because it blows right across that opening. Because today it's not very far. But reflection cares because now it's got a second surface it can bounce off of. So instead of bouncing off of one surface, it's really bouncing off of 2 from that open on the reflection. And so in this case here, this is what my connector looks like. And it's probably pretty deep, and which is, for me, it's pretty decent shape, because, like, again, I don't have the best fibers in my network here because of all the training that I do. But if I unplug this, and this side over here, I didn't clean this side. All right, I didn't clean this side at all. I'm going to go and plug it in. So now it's plugged in. I'm going to unplug it. And then we're going to relook at this side here. All right. Oh, and one thing that I like to do, I don't like changing the tip. So I always use the bulkhead tip. And if I need to look at a bulkhead, I look at a bulkhead. If I need to look at a tip, then one of those bulkhead accessories that I talked about, you would pop onto here, and then I can look at this. It's easier to change the bulkhead back and forth and drop them in the sand and dirt than it is to change these things off all day long. All right, I'd rather just do that. So in this case here, I'm looking at the bulkhead. So I'm going to go in there and I'm going to press this button here, and then we're going to look at it. And this is cross-contamination because I didn't clean the other side. Anytime you see any kind of this circling effect here, this is cratering. The other side had a lot of contamination here, and when we pushed them together, it cratered out. All right, so this connection looks pretty dirty. but it's probably mostly oils, right? And so if I were to test this with an OTDR, so I'm going to go ahead and normal it back up, right? And then I'm going to go to the OTDR here. Right here. I'll go back to the OTDR and I'm going to do another test. So right now on the OTDR, the connector, well, before was 0.6, right? And so what we added some contamination to it. Let's start and test and see what it looks like. And so now, connector number 2 here, a little bit higher loss. The reflection is not too bad though. So we have more of a loss problem here than we have a reflection issue here. But it is possible. In fact, if I were to do this, I'm going to try to do this. So here's what I'm going to try to do. I'm going to go to real time. I'm not going to clean it yet. What I'm going to do here is I'm going to grab this fiber here and I'm going to try to create an air gap and simulate reflection. It's kind of difficult to do sometimes, but let's see if I can get it done because I think it's important for you to see. No, that's loss. Let me see reflection. Almost had it. Almost had it. Let me see 1 second here. Sorry. This is so important to show. I want to make sure I get it right. So what I'm trying to do, okay, right there. Don't move. Nobody move. So here's what I've done. Well, I moved it again. Now it's got some loss issues. So basically what I'm going to do is I'm going to reshoot this and see what it looks like. We might get lucky here, and this might be exactly what I'm looking for. So I'm going to go ahead and reshoot it. The taller the spike, the worse the reflection. So I'm going to shoot this real quick. And we're going to look at event number 2 again. Event number 2 is point. This is perfect. Okay. Couldn't plan it better. So if you look at this, event number 2 has 0.19 dB of loss, which is really good for a connector. But the reflection is tanked. This is an example of how you can have good power and bad reflection. And I did it by creating an air gap. You can see that. If you only use the power meter, you would not have seen this issue because the issue wasn't power, the issue was noise. And so if I go to summary here and look at my ORL is 21 dB, which is awful. This is service affecting stuff here. All right, this is service affecting stuff here. My loss at that location is not bad at all. It's pretty good. And so what's happening here is I have an air gap. And these air gaps are often caused by contamination, or it's not fully seated, or sometimes the bulkhead's damaged. And so how do you fix this? Well, that's pretty simple, right? For us to fix this, we would essentially go to this connector, and of course we clean it. So we already know it's dirty. So I can use a 1-click if I want. In this case here, I want to use the method that I like. I'm going to pull out more of this dry tissue. If you do a lot of cleaning, which I hope you do, then getting a canister version of the cleaning solution. There's different vendors out there or whatever. If you're using a 99% IPA alcohol, you want to make sure the single-use ones are better because as soon as you open a jug of the 99 alcohol, air gets in there and it starts to go flat. It's like we have a 2-liter bottle of 7-Up, and you drink a little bit of it, then you put it in the fridge. You drink a little bit and put it in the fridge, and then it starts to change taste, right? It's changing taste because air got in there and it's changing the properties, right? The CO2 is bleeding off into the atmosphere and it changes the flavor. That's essentially what's happening. And so when you're using 99, you want to make sure and not expose it to the atmosphere. So the single-use packets are pretty good. I like these aerosols and stuff because it keeps everything in there, right? Everything's like sealed in a way. So basically what I'm going to do here is I'm going to go ahead and just, put a little bit of the cleaning solution there. And I'm going to go ahead and, again, hold in the dry and pull into the, or hold in the wet for a second and then pull into the dry. Just do this a couple of times. Right? And normally I'll clean the bulkhead side first because that's the side that's not moving. And then if my depth perception is all right here. And I didn't touch that side, so I'm going to go ahead and use that side here and do the same thing. You want to make sure don't oversaturate it, because then it'll build up on the sides and kind of pull back down. So that's all I'm doing here. It doesn't take long, but I tell you what, it really matters. Having these good type of habits, right? So anybody who does woodworking or does just any sort of craft work, there's certain things that is a must, right? You must, I got to use Loctite on this bolt. I just have to, because that's the best way to do it. To me, this is the best way to do it, as a hybrid method, if you can do it. Obviously, in certain situations, it becomes, it might be a little inconvenient, but I think it's worth the effort. And so now we have this connection here. If I were to go back and test it, unless I really screwed it up, which, hey, it's been known to happen. And so now we see here that we have more loss. See, I screwed it up. Look at this now. I think I created more loss here. No, it's better. So I think that's about as good as this connector gets. This 0.75, because I've cleaned it a million times, and it's usually between 0.7 and 0.8. So normally that would have been all right. I think it's just from the pitting, and I'll show you a slide on that, on how the pitting does that, right? And so it's really important to understand. Sorry while I drink my Fiji water here. So I'm Micronesian, if people don't know that, and so we like our Fiji water. Fiji's not Micronesian. But so basically, you can see how this is, we got good reflection now, and we got good loss. Now, this issue was because of an air gap, but the air gap has to be caused by something, and it's typically contamination. So we resolved the reflection problems, and we already know what the loss problem is, because I know this connector has seen better days, and one day I'm gonna have to replace it. But it's good for demonstration purposes. And so that's why it's important to understand, how these tools work and some of these issues they're gonna have. But even a step further, I have a video that I did on YouTube called How to Clean a Connector with an OTDR. So for those of you that work in a head end, or for those of you that have to test multiple connectors, this is really valuable for you, is with an OTDR or OTDR-like technologies, especially when you're turning up new service. If I had multiple tie cables inside my head end or within my office, I want to make sure and test every single one of those connections at every single tie cable before I turn up a new service. You have to make sure that the fiber is dark for most OTDRs. We do have a version of the OTDR that will test while there's light on the fiber, and I'll show you that. But essentially, just imagine if, let me see here. So let me get it back over here. Imagine if this was, in fact, I'm going to zoom in. This will be better. I'm going to zoom into right here. So this here is my launch cable. Let me draw this. So this is my launch cable here. So this portion right here is my launch cable. It's important to have a launch cable because that separates the FTP. And so here is my first fiber. And I want to test as close to the equipment as I can get. If I can test the jumper that actually plugs into the card, that's what I want to use. So we'll say that this is the jumper that plugs into the card. And then now you have two tie cables here. You have one here and one here. As you see, two peaks. I have another tie cable here. And this one right here is the OSP patch panel. Right? And then all of this is OSP. So if you're a central office technician, or a head-end technician rather, sorry, or even a central office technician, if there's folks from the telco side on here, you care about your four walls. Right? You care about your four walls. So here are my four walls, within my site, right here. So I'll just set it outside, just so it's easier to see. And so if I'm taking errors on a system and I'm able to take the light off the fiber, or if I have an OTDR that will shoot while there's light on there, I can look at this and I can tell which connectors have the most loss and which connectors have the highest reflection. This one has the highest loss because from here to here, you can see it drop. This is that 0.8 or 0.745, right? But if I don't have a power problem, that's not my problem. That's something that, if I can resolve and I'm there, I can resolve it. But if I'm working a maintenance order, what you have to be careful of is just because something is outside of your pass-fail thresholds doesn't mean that that's what's causing your issue. In this case here, this 0.754, while it's above the spec that I would prefer, it's 0.25 dB out of spec. If you have an outage because of a 0.25 variance and loss, you have a problem. But you've already measured the power and you know the power is good. So we're not really looking for loss problems. We're looking for reflection problems. And what has the highest reflection is the tallest spike. So if I go to this location right here, this has the tallest spike. I'm going to clean that. I'm going to inspect and clean that connector first. And so that's going to be jumper, first tie cable, the second side of the tie cable. So most likely what's happening here is you have a panel on this shelf, you have a panel on this shelf, and we're going from here to here. Because this is going to a different cable that way, and this is going to a different cable that way. Because it's very short. You can see 3 and 4s. Well, it's not shelf short. It's 558 feet. So about 500 feet difference. So it might be, this side of the rack and then the other side of the rack, one's going, going upstairs to downstairs or downstairs to downstairs, whatever. But now you know which side of the tie cable to clean. Instead of just cleaning everything until the problem goes away, I'm going to clean that one first. Then I'm going to, if I'm still taking errors, I'm going to clean this one. So I want to bring this one down, and I want to bring this one down, right? So by cleaning the connectors. Now, unfortunately, I don't have easy access to these connectors. They're in a box. But I have easy access to this one, but we've already improved that one. But if you look at it, it's a neg 57. And I want, this is a good reflection. Most systems don't have problems until they get below neg 40. This is also all right. And so the one that has the highest is number 4 here, and it has a neg 46. I would clean this one first. So that's how you can use an OTDR or some sort of a reflectometer to troubleshoot connectors, which is why I talk about that, because that's really important to understand. And again, this is still all the Fiber 101 stuff, but you see this is all the analysis stuff. And so, so from that perspective, that's how I like to use an OTDR. We'll come back to some of this OTDR stuff here, because I want to show you that, there are other tools out there. And so depending on what your use case is in your area, so you might have, let me see here. I had to charge this one. I left it on last night. See if it's enough charge here to turn on. Sorry about this. I'll turn this one on. There we go. And so I'm going to have just a slew of test equipment here in a second. This is the source. We'll talk about that later. We already talked about the power meter, so I'll put that over there. We'll be using the probe the entire time because it's important. So there are different types of devices out there. So this is an OTDR. Over here we have an OTDR. It's like, I feel like Oprah. And there's another OTDR. They can get pretty small. So this is a full-blown OTDR as well. All right. So there's different versions of OTDRs. Sizes and specs and dynamic ranges and whatnot. This one looks like it might be dead. Oops. And this is an OX1. So some of you might have this. This OX1 is not really an OTDR. It does OTDR-like stuff, right? So this is a kind of a go, no go meter. So it's a great first line troubleshooting tool. And of course it's smaller. It looks the same as this. This one over here is a full-blown OTDR as far as specs and resolutions. This one is we call it a fiber multimeter. And so basically, if I want to test the fiber, I would inspect and clean this. I'm not going to, I'll clean it real quick. I'm not going to inspect it just because of the sake of time. And this one right here has actually seen better days as well because I've used it for a couple of years. But I'm going to unplug my fiber that I need to test. And I'm going to go ahead and plug it into here. And so this is where it's important, to understand. And so this one has 3 modes. So if you want like a quick, hey, is this good or bad? It's like a quick check. It's like a 4-second test. You press this button here and it reads it. If there's any incoming signal, it'll also measure the incoming signal. So this one can test live fiber. And so in just a couple of seconds, it gives you this star review. Anything 3 stars or better is good. And so it gives us our key performance metrics that we care about. What is my length? What's the loss and what's the ORL? So if the loss is within my budget, then I'm good. If my ORL is 32 or better, then I'm good. And so this is like a quick go, no go. Now, if it failed ORL, then I can go to the link mapper. I can switch it to this one here, which takes a little bit longer. And this one will do a comprehensive check. It'll look like an OTDR shot. It functions like an OTDR, but the specs are not as tight as the OTDR, right? Accuracy, repeatability, distance. This is only good to about 40 kilometers. And so knowing what tools you have and how to use them and when to use them is important. That's why we talked about a lot of the Fiber 101 stuff, because now when we start doing these tests, we can analyze the results a little bit better. I'm going to plug this thing in so it charges. So because I work for the manufacturer, I have a second one. So yeah, I had fiber installed for the first time after 30 some years in the industry, 34 years in the industry, I think. I finally got fiber to my house, and it was about 2 months ago. And the look on that technician's face when I busted out all my test equipment was something I wish I would have captured on video. I have a lot of test gear. So anyway, so here's the test over here. I'll let this one start out. But here's the test here. So we still get the metrics up here. And if I had incoming power, it would have measured the incoming power. So I would have known whether my light level is good, whether my noise is good. And so here, this is where I can start clicking on elements, right? So now I got these, I can see the splices and connectors. I can click on them, and it'll tell me what it looks like and what it's like. I can scroll across. And so you can do the quick go, no go as soon as you show up, and then switch over to, a more advanced fault isolation stuff. And so having tools like this and understanding how they work and where they come into place is incredibly important. Again, I always start with fiber inspection and power because everybody has this. All right, everybody should have this. If you don't have the minimum of fiber inspection and a power meter, then you're really not arming yourself for success of resolving that issue. And then secondary to that, you can look at different tools like an entry-level go, no go meter that gives you splice information that's for short range. So this might be something more for a tech that's closer to the customer prem. All right. And then if you need more of a full-blown OTDR, but you don't want to haul something that's really heavy, then you can get a full-blown OTDR in a smaller package. Right. And this one will test as far as this one over here, believe it or not. Right. It's just in a smaller package here. And if you want something more full-blown that has modules so you can do multiple different types of testing, then you go to a different one, right? So understanding what you need is important. And so I'm not going to run this OTDR because we've already been running OTDRs the entire time, but it's important to understand these different tools. And so these, you can kind of see how we're tiering the testing. And then over here, I have a visual fault locator. There's one on here as well, and then there's one on here as well. I got visual fault locators all over the place. But this is a handheld one that I like. Most of these will only go about 3 to 5 kilometers. We just released one that goes to 20. You can go higher than that, but you're getting into laser safety issues, right? If you have a VFL that'll do 60 kilometers or more, it's probably overpowered. And you have to be careful with those types of VFLs because the power level coming out of them, if you're too close to a transceiver, you can actually damage a transceiver or disable it. There are some systems, like a lot of fiber to the home and PON systems, if too much light comes into the OLT, it'll disable itself to protect itself. And so you're out there troubleshooting, and now you can't figure out why you have no light. You have no light. You got to log into the OLT and re-enable the light. So, but if you have DWDM optics, which I know you do, and you have CWDM optics, you got to be careful with if you're testing too close to those types of optics, because you can actually damage the transceiver if you're too close, not just with a VFL, but also with an OTDR. And so VFL is pretty self-explanatory. It's a great way to do continuity testing and those types of things. You can have it blinking, not blinking. So blinking to me is the easiest one to find. I mean, to locate visibly. You can have a continuous or however you want to set it. And again, this is for visual inspection. This is also useful if there's a broken splice or connector. It'll shine out through the jacket. So within this jacket, if I had a break in this, it would shine out red here, right? You would see that red. If there's a pinch, you'll see it as well. In fact, I think I have a picture somewhere. See if I can find it real quick. Let me find my pictures here. Fiber pics, there we go. I think I have a picture here somewhere. Let me move it over here so you can see what it looks like. Oops. Uh-oh, there's something going on here. There we go. Oh, sorry about that. I'll get this down here. Where is it at? I just saw it. There it is right here. So now this one looks like it just came back from the club. It's usually not this bright. I don't know what's going on. So but here obviously you see a macro bend, because when you pitch a fiber, you break how the signal travels on the fiber, and it wants to bleed out of the cladding. And when it bleeds out of the cladding, it'll line up like it'll shine like this. If it's a splice, the splice will just flash. I mean, if it's a broken fiber, if you got it on flashing, it'll just flash, which is pretty important. And keep in mind, you want to minimize these bend radius issues. So this right here caused a protection switch. So the technician, or somebody ran the jumpers, and I guess when the technician went to go turn it up, they needed more slack, so they pulled on it, not knowing that there was a zip tie mid span in the raceway that they pulled against. And when they heated up the Raman amplifier, it burned the fiber. So that's amplified. Here's another one burned from a Raman amplifier. And EDFAs can do the same. I think this one here, this is an no, this is actually still a Raman, but EDFAs will do the same. So this is what a burned connector looks like. So if you have contaminated connectors and it's plugged into an amplifier, even an EDFA, it could fry it. And so again, for safety purposes, you got to make sure that you're aware of what's on the system, because quite frankly, if there's an amplifier on there and it doesn't disable itself, it'll smoke. This is a very common thing that splicers will see, unfortunately. And so it's eye-opening for you, on some of those things. But so I want to talk about that, because of course that's macro bending and some of the other things that cause issues, right? And so being aware of that's really important. So in this case here, we don't have any macro bends or pinches. We talked about that already. But from the VFL perspective, again, that's what this tool is good for. It's good for tracing stuff out, so you can see the other side. It's good for looking for problems. If there was a damage in the boot, which is common, and usually it shines, there's some subjectivity to it. So I always like to compare it to another jumper to make sure, well, maybe that's just how that jumper, looks when you put light on it. But this is an incredible tool to have, right, as well, for troubleshooting. And of course, you can put it on one end and go to the other end and find the other end coming out. And because it's small, you can store it away, and hopefully somebody doesn't take it with them. So now we've used the OTDR to kind of troubleshoot that. It is important to understand some of the limitations of an OTDR. So I'm going to go ahead and let me just plug this one back in real quick. Oh, also with APC connectors, you see the thumb, there's the key there. If you put your thumb on the key, this is where the angle is at. So this is where the angle is at right here. And so when I go ahead and use this, I'll put my thumb on there, then I'll hold it towards the angle, and then pull down. All right. Again, I'm using the cleat top this time or the real cleaner, because it's convenient and saves me time right now for this training. But if we go back to the OTDR here, switch back to the OTDR. It's important to understand the settings in an OTDR and how it can really throw you off. And so with an OTDR, when you increase the pulse width, you can test further, but you lose resolution, right? So you can test further, but you lose resolution. In fact, I think I have a slide on that. Let me find this slide. I know we haven't gone back to the slides in a while. A lot of the stuff that are on the slides are what I just showed you. So we skipped some of that. But if you look at an OTDR sends out a pulse of light, right? It sends out a pulse of light and it reads the backscatter, is essentially what it does. It'll tell you if there's a backhoe sticking up out of your cable. It'll tell you where the squirrels are having lunch, those types of things. Opens, high reflection connectors, which is what we troubleshot. Macro bands, which we showed you that as well. But it maps out the entire system for you. But it has some limitations, and the biggest limitation is resolution and pulse, and understanding that. With an OTDR, as you increase your pulse width, you can test further and further. Now, be careful with this table. I use this table because it's one that we had built. But at the same time, this table is relevant to a specific power range of OTDRs. So different OTDRs have different power ranges. This one's specific to a long range OTDR. So yours might not shoot as far, or it might not, or it may shoot more if you got a higher power one. But as you increase your pulse width, you can test further. And the pulses are measured in length. So if I have a 5 nanosecond pulse width, my pulse length is a meter. right? So I have a meter pulse. That's also my resolution, my sampling. It's associated with that. There's more to it than that, but for easy conceptual purposes, that's what we use. So you have a 1 meter pulse. So you're sampling the fiber about a meter at a time, which means you get good resolution. You can see things that are very close together, but you don't have very much range. And after every reflection, after every connector, we have something called a dead zone. Here's that spike. This is your dead zone right here. It's a section of the fiber that you can't see because you can't see either. My big head's in the way. And so that's your dead zone, right? So as you increase your pulse width, your resolution, your sampling gets longer, and that section of fiber you're blind to gets longer. And so this is going to be really important. I'm going to show you this in a minute. And so when you start, and I'm just like moving myself all around here. As you increase it, you can test further. So if you're shooting a 100-kilometer span or so, you might be using around 500 nanoseconds. That's going to be 102 meters, which is roughly 300 and some feet of resolution. And then it's going to have about 63, 65 feet or meter of dead zone after every connection. And I'll show you what that looks like on an OTDR trace here in a second. But to explain resolution, we're talking about these now, right now. So if I were to shoot a trace at 5 nanoseconds, which was high resolution, short pulse, I'm going to see that there's 2 connectors here, right? I'm going to see that there's 2 connectors because I'm using 5 nanoseconds. But the problem is it's noisy at the end. So I have to increase my pulse width or my averaging time to clean up the end. So I go to 30 nanoseconds, but now I only see one big event because it merged them. But I'm clean over here now. If I can see an event, if I can see a splice at 60 miles, I can't see a splice at 60 feet because the pulse width I need to get to 60 miles is longer than 60 feet. This is why sometimes you do a short shot and a long shot because you can either see far or you can see close up. You can't do both with an OTDR, right? It's like a camera. You focus out there or you focus up front. So unless you do something different, that's how that works. And it's also the resolution. So if I have a 5 nanosecond pulse width, it's able to read 2 splices that are close together. If I have a 10 nanosecond pulse width, all of a sudden I see one big event. So on the OTDR trace, you would see 1, 2. Here you'd see, and it would just be a big one, right? This could be 0.1. This could be 0.2. This would be 0.3. This is what it looks like on an OTDR. So I'm going to switch back over to the OTDR here. Range, pulse width, and duration. Range is how far you can test. Not how far you test, how far you see. So when we set it for 32,000 feet, it sets this to 32,000 feet. If I'm testing 60,000 feet, it's just going to run off the screen, right? So this is display range, not test range. Then there is, pulse width, and pulse width and duration work together. As you reduce pulse width, you can see events that are closer and closer together, but you can't test near as far. Duration allows you to clean up the noise. So it allows you, as you increase your duration, you're able to get away with shorter pulse widths because it cleans the noise up. But there's diminishing returns. If I'm doing maintenance testing, I almost always use at least 60 seconds. At least 60 seconds. Because I want a good averaging time. I'd rather spend more time. I'd rather wait an extra 45 seconds for results than speed up my testing and don't get good resolution and am not testing in the right place. That's what I don't want to do, right? And so to kind of show you this, I'm going to do one trace. 100 nanoseconds is a typical trace for, head-end to head-end type of testing, right? Site to site. I'm going to go ahead and hit start. And so this is going to clean up really fast. boom. It flattened out pretty quickly. And so, get myself back over here. Hopefully that's the last time I move my head. So if you look at this here, I got 11 events. All right, if I go to event number 4 here and zoom in, you see I got one big event here. There's this weird side hump over here, right? So just remember that. And if I go over here and zoom in, I got one big event. And so I'm showing 11 events. And it, seems, hey, I'm getting results. That's good. But look how far up over the noise. Here's my noise floor. And this is how much margin I have. This should be down here somewhere. So if I drop my pulse width down considerably, if I hit start here, it's going to launch lower down on the power scale, but it's going to be noisier. Because I didn't give it enough time to clean up because I used 5 seconds. This is where duration comes into place. So I'm going to increase the duration to 15. I'm going to retest it. And hopefully that cleans up the noise that's going through there. So we'll see if it gives enough time. Getting a little better, a little better. So it's better. I'd probably add a little bit more just to get a little bit cleaner. And now I have 12 events instead of 11. In fact, if I go over here and look at this one here, we got 2 events. And remember, before it looked different. Before it looked like this. Because I had a higher pulse width, higher power. Higher power, the more it merges stuff together, and the bigger the dead zone. And so this is a problem that you're going to have, and you're going to have this problem for several big reasons, especially inside of the office. One of the big problems that we're seeing a lot right now is they have these modular FDPs, that sit inside of your panel. And these modular FTPs, in fact, let me draw it this way. Let me just get rid of that and do it all over again. These modular FTPs, we'll say right here. So we'll look top down. And essentially what you're going to have here is you're going to have, depending on your connector types, right? You might have a bunch of, LC duplexes here or whatever it happens to be. So this is the front side where you plug in your equipment. So you have all of these fiber ports, and obviously it's not perfect. And so we'll say there's 12 of them here, right? And so this is where you plug in on the front side of this panel, where you plug in your fiber. And of course, these all go through and then come out over here. So all of these here, this is all the individual fibers that are, inside of the tray. And here, we're not starting to see, we see a lot of these. MPO connectors, multi-fiber connectors, these 12 fiber MPOs. So they're like tethers. So what they do is they have these modular FTPs, they slide them in, and they plug in the trunk cable into the back. Sometimes it's fused. Fused is better, but it has its own complications. And usually this tether will run all the way out and it's spliced somewhere. The problem is the distance here is only a couple of feet maybe of fiber. When you shoot it with an OTDR, if it's too short of a distance, the OTDR can't separate the two. So when it's testing, what the OTDR is going to do is it's going to look at it and say, okay, I have this first connector here. Of course, I have this panel that it's in, and I have this MPO back here. All right, and so we have all of our fibers that are coming out of this and looped into this thing, right? On an OTDR trace, you're going to see this. If this is only about 1 or 2 feet, you're going to have your launch cable. Then you're going to get your spike. That's a bad place to draw. Let me try it down here. You'll come in here. You'll see your connector. It'll come up. You got my reflection, and it comes down over here. Because the pulse width is not short enough to be able to separate the two connectors. And so if you're seeing, hey, I got 1.0 dB of loss, well, that's good, because that's 1.0 divided by 2 connectors, because we're measuring 2. But here's the worst part. If my reflection is bad, and you clean and clean and clean this LC connector, and this number is not getting any better, it's because this one here is your neg 30 dB reflection. And this here is your neg 50. The OTDR cannot separate them. They're too close together. So if you ever come into a situation where you clean and clean and clean, you can't get it any better, see if there's an MPO on the back of that thing. If you can safely look at the back side of that cabinet, see if there's MPO connectors back there. We see this a lot with different types of systems. A lot of vendors do it right now, and there's reasons for it. But if you have modular FDPs, if there's an MPO on the back, you're not going to be able to separate. Here's the downside. This is 12 fibers. If you already have traffic on the first 2 fibers, to clean this jumper, you got to take down the live traffic to do it, right? So this is where during construction and installation that it's critically important to make sure that you inspect these. But the MPO connectors, most of the companies are trying to do a better job of shipping those cleaner because it's become such a big, customer service issue for them. And so open up the cap, inspect it. If it's clean, plug it in right away, right? If it's not, then you're going to have some sort of cleaning device. And of course, with MPOs, this is important to understand. You may not think you have MPOs, but you do. You just didn't know you had them. You got to make sure and get like an MPO one click, if that's the case. So for those of you, especially within the office, look into that. If you start getting into higher speed optics, like parallel optics, 800 gig. So I'm doing a lot of 800 gig right now. I do all of our training for high speed as well. So if we ever want to do one for high speed Ethernet or high speed optics, we can do one as well. But parallel optics for 800 gig uses 16 fibers. It's got 8 transmits and 8 receives. They're using primarily MPO, right? They're primarily using MPO connectors. And so 8 out, 8 in. And there's an MPO 24. And there's other new connectors like MMC 16. These are multi-fiber connectors. And of course, once you start getting into that, then you have to look at the fiber inspection tips for it, the cleaning solutions for it, the bulkheads for it, all of that stuff. So just keep that in mind. Not everybody's going to run into it, but I think there's probably going to be some folks on here that are definitely going to have that issue or run into multi-fiber connectors because they're here and they're more and more prevalent. We see them a lot in the data centers right now. So I'm doing a lot of data center work right now. A lot of the AI data center stuff. I'm working on that as well, and we're seeing a lot of MPO connectors. In MMC 24, which is a 24 fiber small form factor, they call them VSFF, very small form factor. So these new connectors that are even smaller than LCs, they have more density. If you have duplex LCs, and I'm gonna create some numbers here because I don't know the exact numbers. But if you have duplex LCs, which is very common, in a 1 RU rack, you have a 1 RU rack, 1U rack, this is about 288 fibers you can fit in that space, roughly. If you go to MMC 24, which you're not going to have right now, I don't think, unless you have it in your data centers, right? This is going to be 6,500 plus fibers in one RU. So the densities are getting pretty crazy. So just as the technology evolves, try to stay ahead of it wherever you're at. Because especially if you're sourcing tools and equipment, you're going to need to make sure you get your jumpers, your bulkheads, your attenuators, your fiber inspection probe tips, all those types of things are going to have to scale with that. So just keep that in mind when when you're looking at the different technologies that are out there. And so back over to the deck here. Back over to the OTDR. So now when I zoom in, like I said over here, we have these two here, right? We can clearly see that there's 2 events here, and what the values of those 2 events are. If we had what we had before, which is this right here, and it was a neg 30 reflection, and you didn't know there was 2 connectors. This is why it's really important to know your network. You would walk over here and clean this connector, clean it, clean it, clean it, still neg 30, still neg 30, still neg 30. The problem is 131 feet away is another connector. That's the one that's dirty. That could be in somebody else's cage, whatever. So you have to make sure and optimize your settings to be able to see that connection. And in fact, there's an advanced tool that we have that does that. Right? It's called IOLM. And so there's no pulse width, no range, no resolution. I start up IOLM here. And this is an OTDR. It's just using advanced software and a little bit of hardware. With an OTDR, 5 nanoseconds or 10 nanoseconds, one or the other. You can't have both. Not with a standard OTDR. There are some OTDRs that are different. For us, being different is IOLM. IOLM does multiple resolutions, so 3 nanoseconds, 5 nanoseconds, 10 nanoseconds. And then it analyzes what's good at each wavelength, at each pulse width, at each wavelength. And it remembers it and it compares it to, and then it runs a test and it compares it. So you'll always see something at 60 feet and you'll always see something at 60 miles, right? Because it doesn't suffer from that type of thing. And it also has analytics. And so if I were to go in here to our favorite connector here that's seen so much abuse over the years, turn this off and turn this off, sorry. So this connector here that we've seen over the years, I'm going to go ahead and put a pinch in there again in that connector, just like we did before. And then when I go back over to here, if I have a launch cable, you want to null it out. You always want to use a launch cable. With IOLM, you can use 20 meters. With an OTDR, when it comes to launch cables, the longer the pulse width, the longer the launch cable, right? And so, so in this case here, I'm not going to null out the launch cable on this one here, but normally I would null it out. You would hit this button, you'd plug in your launch cable, inspect, clean if you need it, hit calibrate, and then it would measure it out for you. In this case, I'm not going to do that because I don't have a ton of fiber, and because I put a pinch at that location. So I got a pinch there, and then I'm going to do a quick test. I'm going to change the test that I'm doing here. I'll do this one here. So IOLM is based on configuration. So you set configuration so it knows what's good or bad, right? So you load a configuration, you select your wavelengths, and you hit start, and that's it. Right? There's no distance, no pulse width, nothing. And it's going to go out there and analyze the fiber at those 2 wavelengths at multiple resolutions, multiple pulse widths, and then give you the most comprehensive view of your fiber. And so, and it does a really good job of it. There's a lot of algorithms behind it. So as it's ticking away here on the status, once it's done, it'll beep. And now we have actionable items here. So here's my launch. If I click it, we can measure our own launch. And if I click on this one here, it tells me something, right? It tells me inspect the fiber in this area for and to search for excessive banding or cable compression. That was that pinch I put. If I click this, it'll tell me the loss. So everything, these are all green because they passed. If I keep clicking over, I have something over here. This is actually not a splice. This is APC connectors can have such low reflection that they look like a splice. So here we say, oh man, I got a failed splice. No, we don't. If you notice this is 150 meters. This is a 150 meter receive cable that I put in there. 150, 500, 1.5. So you can see all these are all close to each other. So in here it says, make sure that the fiber is properly spliced because it thinks that this is a splice. It's not a splice because I know my network. But it also says this loss could be due to a low reflection APC connector. Change element type if you need to. I can go in here and say, you know what, this is not a splice. This is a connector. So look at it like a connector. And it did. So now I got to pass. So the only problem I have here is I got to go find this pinch. I don't want to unplug this fiber and clean this connector yet. It could still be dirty, but I know there's a pinch because I can look at this. 1550 is higher than 1310. I'm going to go over here and clean fibers. Right? And so this is a pinching problem. And because we understand the 101 stuff, we understand how this works. And so, again, back to your tools, that's why it's important to understand, what the different tools do and how to utilize them, effectively. And so now we've done everything from we've measured light levels as our first, our first line of defense during maintenance issues. We got good light levels, and of course for turn up as well, right? For turn up, because you want to measure your light levels to check what your receive power is coming into your fiber node or your different remote fire devices and stuff like that. If it's coming in too hot, then you need to put a maybe an attenuator on it. So this is something that you use for initial turn up, and of course you'll be using this during the entire life cycle. So if you get a call to troubleshoot an issue, the first thing you want to do is bust this out to see if you get light. If you don't have any light at all, then you get out some sort of device like an OTDR or an OX1 or whatever to map out the fiber to see where you're having issues. Is it a cut, or is it something else? Is it an equipment issue? Is it a fiber issue? This is your next line of defense. And of course, the entire time you're using a fiber inspection probe, right? And there's different fiber inspection probes out there depending on what you use. And so it's important to have what you need. So fiber inspection probe and power meter all the time. Having extra jumpers and extra couplers and all the appropriate cleaning tools are going to be another part of the whole thing. Having the appropriate tips, right? I have a whole box full of tips over here for different types of applications, depending on what I have. And also I have, this one's for checking LC, so to check both sides of the duplex LC at the same time, which is pretty handy. And I got ones that do NPO. I got ones that go around corners because sometimes, some panels are not easy to inspect. So now we got to build stuff to go around corners. And so there's a lot of different ones in here that you can use. So you want to make sure you get appropriate ones for that and you're using the right ones for that. And then at that point, everything else is just going to be standard troubleshooting stuff that you see.
I have a question from the audience.
Sure.
The question comes from Oscar Moreno. Can a high-powered BFL damage a MUX?
Not a passive MUX. It would have to be, some incredible power. So, MUXes are normally passive. Now, if it's the optics transmitting down the MUX, then absolutely. So if you have, say, a transceiver that is a specific ITU wavelength that is transmitting to the MUX, if you shoot into that transceiver, you can definitely damage it.
Thank you, Kevin. Just a reminder, we have 3 poll questions queued up, ready to go whenever you are.
Let's do that real quick here.
Okay.
Yeah, go ahead and queue those up.
Let me start with OTDR. So I'm going to put this one up for the audience to answer. So if you guys take a second. Oh, why isn't that? Now I'm having technical difficulties again. Hang on a second.
That's all that was worse. No problem.
Yeah.
And kind of a segue off of that question about the high power. Within our IOLM, we have a test configuration.
Oh, there it is. I did get it up.
Okay, perfect.
Yeah.
Hold up! Look at that fanciness there. Let me see. How do we get to that?
So this is an important question, and Kevin did cover this earlier in the webinar. So I hope everybody can see.
I saw a notification before, but I don't see it. But maybe I'm not supposed to see
it.
So.
There it is. We've got some.
Okay.
We've got some answers coming in, so looks like.
Good deal.
Yes.
So what was the poll question?
Poll question is: what length of launch cable should I use, and does it change depending on the network I'm testing?
It varies. Okay, can I go ahead and answer, or is it people still?
No, we're still collecting responses, so we'll just give it another minute.
Sounds good.
We've got about 31% of people have voted. So again, folks, vote quickly, and we will get to the answer right away. It's still climbing a little bit. When it stops, I will close it.
Sounds good. And it kind of felt a little bit of error. So the question about damaging the optics that I talked about, they talked about, the question was specific to MUXes, but I kind of converted it to the the ITU channel coming out of the transmitter. So within IOLM, we have a configuration called, let me see if I can find it here. You know what? Let me, oh, you know what? That's because I don't have
it looks like our responses have slowed down. So I'm going to go ahead and I'm going to display the results, I think. Let's see here. Close. Okay, let's see, share. Okay, I don't know if you can see this, but so the first question, launch cable should always be 150 meters. 23% picked that answer. Launch cable isn't necessary. Only 3% selected that answer, and depends on network and pulse width. 77% picked that answer, which is actually the correct answer. Let me confirm with Kevin. Is that correct, Kevin?
Yes, it is. So pulse width will vary depending, launch cable length will vary depending on the pulse width. So the longer the span, the longer the pulse width, the longer the launch cable, right? And that's a very important question. For most folks, 150 will hit most of your needs. But once you start getting over a certain distance, then you'll need to start looking at getting longer and longer launch cables. In fact, this is one I don't normally show this one here because it's not 1,000% accurate. This is pulse versus launch for commercially available launch cables is what it is, right? So most folks, they're good with 150 till about 1 microsecond of pulse width. After that, then you have to go up to longer launch cables. Now you can get away with shorter ones, but this was just easy, kind of relating it back. There's math you can do, but at the end of the day, to determine whether or not you have a good launch cable, what the launch cable looks like, is really look at the OTDR shot. And when you shoot the OTDR, you want to be able to see the first connector after the launch. You want to be able to see the end of your launch cable. So I can see the end of my launch cable. It's right here. If I didn't have a launch cable, or if I didn't see it, then I oversaturate. It means I need a longer launch cable. And launch cables are important because if you look at the first connector, and now I'm shooting a fairly, so if I look at this first connector here, and I zoom in on it, and I measure my dead zone, I have 24 feet of dead zone, which means if I had a jumper, if I had a test jumper less than 24 feet, I would not be able to separate my FPP from my test port. So you want to make sure that, that you have a launch cable and the length is sufficient enough so whatever pulse width you use, you still see that first connector. And again, 150 meters is going to cover most folks.
Okay, yeah. I have another poll question. We'll get to that right now. So the question is, can it? Let me move something around here. I can't see it all. Can attenuation alone tell if a fiber link is good, or do I always need to check reflectance too? So.
Yeah. So that's a great question. Of course, we covered that. And we talked about it quite a bit. Yeah. So hopefully we'll.
We're collecting responses. 24% have voted, so we'll give it a minute.
Good deal. I almost answered. I forgot they were gonna do.
Yeah, I think we covered it quite well, so I think everybody should. Most people will know this answer. So I closed it, and 97% answered always check both, which I do think is the right answer. Correct, Kevin?
It is the right answer, right? If you have the tools for it, it's definitely important to check both. And I know not everybody's going to have some sort of way to check reflection, but if you do, absolutely use it.
So we have one more question I'll ask the audience, and then we'll let Kevin wrap things up here. So what's the difference between reflection and ORL, and why do both matter when qualifying a link? So you have two options. they are the same, single event versus cumulative. So this is an important one. Kevin covered this in detail. Hopefully, I had to reword some of the questions and answers. So hopefully, I got these right, so it's not too confusing.
Sounds good. Sounds good.
So we got about 35% of voted. So we give it just another minute here. Okay, I closed the poll, and wow, 100% of the folks answered the correct answer, single event versus cumulative. And I have to say, even going back to the metallic TDRs, the one thing that I think that many of us make this mistake is we don't really pay attention that much to the ORL, but we really should. So
Yeah.
it really tells you another story. And if you're not paying attention to it, you're really missing stuff.
Yeah. Absolutely, I agree. And like I say, if you have the tools for it, it's important to make sure that you're looking at your reflection in your ORL, and ORL being span. It's really the quality of the span. When it comes to the interaction with the signal. And like I said, I know not everybody's going to have a reflectometer, right? But at the same time, just realize if you only have a power meter and a fiber inspection probe, that why you're cleaning connectors, right? Because you have a purpose for it, and the importance of, okay, so I don't have a reflectometer, but you know what? I have a cleaning kit and I have a fiber inspection probe. So I'm going to do this the old school way. I'm going to go inspect my connectors, and if it's dirty, I'm going to clean them. If it's damaged, then I'm going to replace them. But if you do have those tools, just understand the power that those tools can give you to help you minimize the restoration timeline, which is what, at the end of the day, what we're all trying to do, right? Is keep this, keep our customers happy and do as good of a job as we can. And of course, I'd love doing sessions like this with SCTE because I love doing training and teaching. I thought I was going to be a history teacher growing up, but because the value and the importance of understanding and what you do and performing better work for yourself and for your company is really important. So hopefully you found this a useful session. I don't know if there's any more questions, Woody, that we need to cover. I can hang tight for that, but otherwise I'm done with my portion of the presentation anyways.
Just got a comment from Mark Mazurik. Hope I said that right. Thank you, guys. Kevin, your presentations are always beneficial, and I have to say that's extremely true. So I just want to say thank you to Kevin for presenting this important topic. As we get more and more into, our fiber goes deeper and deeper in our plant, and the need to reduce the MTTR during fiber events becomes ever more important with time. So we all need to stay sharp on our troubleshooting techniques and get out there and get those issues fixed before customers get outraged by by outages, and that's easy to do. So we'll close it off there. Again, thanks everybody for joining, and thank you, Kevin. Great job.
Absolutely. Thank you very much, everybody, for your time. I appreciate it.